SwayamPrabha. Digital India. Educated India.
So, we will first start with the case where we place the origin of our coordinate system in the zeta plane at the center of the circle itself, and we take the parameter b to be equal to the radius, and let us say the flow is coming at an angle of attack alpha to this. Now, what will be the transformed geometry? What is the transformed geometry? First of all, you can see that in this case these and these are the two critical points, plus b and minus b. Both the critical points are on the surface of the cylinder or on the circle. Each of these critical points will be transformed to a corner. That angle pi between the two curves intersecting at the critical points will become two curves with included angle 0, angle between the curves 2 pi and the included angle by the curves is 0, as you have seen. So, this point as well as this point will transform to a sharp corner. But what will be the geometry? See, in this case this zeta is r e to the power I theta. Then what is z? Which is two r cos theta. There is no imaginary component. That means, the transformed body is lying only on the real axis in the x z plane, just a straight line, or we will call a flat plate. So, in this case the transformed body is a flat plate airfoil, obviously no thickness, the resulting body has 0 thickness. How much is the length? This point which has transformed to this point, this length is 2 r. Okay. All other flow properties, that is the flow velocity on the transformed plane, that is on the z plane, that is flow velocity over the flat plate airfoil, can again be obtained using those formula that we have already developed. Velocity on the circle divided by that dz d zeta. Pressure can be obtained then using the Bernoulli's equation. Lift, of course, we have already derived that A by C. How much is the lift force? Chord equal to 4 r this corresponds to the upper surface of the flat plate. For the circle, these are the two stagnation points that we have. This is the stagnation point we have fixed at the trailing edge, and the other stagnation point will be say here. Okay. The forward stagnation point will be here, and the rear stagnation point we have fixed it here. Now, let us say the complex velocity. We already had that expression. This we simplified last time with the value of circulation. How much was that? What was that expression? Or you can add that expression 2 I q infinity, it was sin alpha plus beta minus sin alpha minus theta. How much is beta here? Beta is 0. Beta is the angle that the line that joins center to the trailing edge point or the center to the critical point with the x axis. In this case, the center itself is on the x axis. So, that beta is 0. So, this becomes sin alpha minus theta into e to the power minus I theta. Yes. Yes. Sin alpha plus beta minus sin alpha minus theta. Beta is 0. Beta is 0 here. And how much is dz d zeta? So, this gives velocity on the surface of the flat plate at any point. Again you see that this complex velocity also has only a real component. The complex velocity has only a real component, meaning on the flat plate plane the flow velocity is simply along x axis, that is or tangential to the flat plate, which is as it should be, because the normal component of velocity by boundary condition is 0, which was satisfied on the circle. Most often this expression is written in this way. How much it becomes then? Sin alpha in terms of x, if we use x instead of theta, because that might be more convenient to write this as a function of x instead of a function of theta, then what it will be? Theta is the coordinate varying over the flat plate from 0 to 2 pi. Instead we want to use it x or x by c. How is x and theta related? X equal to 2 r cos theta, 2 r cos theta, not r cos theta, and 2 r is c by 2. We will forget about this r, c by 2 cos theta. So, this how much is the velocity at the trailing edge? We know for Zhukovsky's airfoil, trailing edge is not a stagnation point. At the stagnation at the trailing edge, there is a finite velocity. Even though the corresponding point on the circle plane has 0 velocity, that is using this figure. See, this point, the critical point has transformed to this trailing edge point. Okay. This is the point that has become the trailing edge point. At this point, we have forced the velocity to be 0, we have made it a stagnation point, but this is not a stagnation point on the airfoil surface, which we have already derived yesterday. What would be the velocity at the trailing edge? So, velocity at the trailing edge how much? Remember, the velocity at the trailing edge we derived in general is q infinity cos alpha plus beta. In this case, beta is 0. So, velocity at the trailing edge is q infinity cos alpha. Okay. You can get it from these two relations, but not from this. So, is there any stagnation point on the flat plate itself? So, the circle has two stagnation point, one is at this point and one is at this point. The forward stagnation point is here and the rear stagnation point is here. We have seen that the rear stagnation point is not a stagnation point on the transformed plane or for the airfoil. What about the forward stagnation point? Will it remain a stagnation point? If so, where? Where will be the forward stagnation point? On the flat plate, where will be the forward stagnation point? Where it will be? At the origin? At minus r? At minus r? X equal to? X equal to minus 2 r. I mean on the flat plate plane, you mean to say at the leading edge, at this point itself? Then? At r, here in the middle, why it should be? Is it becoming 0 there? If you say x equal to r, which is c by 4, r is c by 4, minus 2 r. No, how can it be? On the think in terms of the theta itself first, what will be the forward stagnation point? For the circle, where the stagnation forward stagnation point is? At theta equal to, just not that this, at what point, which point? Theta equal to? Theta equal to pi plus alpha. Okay, then where is that on the flat plate? Minus 2 r cos alpha. But W should come 0 if it is stagnation point. So it is not at pi theta equal to pi plus alpha, but where it is? You know the expression for W, either you can make it 0, you can find out at what theta it will become 0, at what theta this will become 0, or where is that point going, that theta equal to pi plus alpha on the circle, theta equal to pi plus alpha on the circle, where it is, what is the point it is being transformed to? Is that again theta equal to pi plus alpha? Or let us say forget this, perhaps this is easier. W equal to 0 for what value of theta? Yes? solve this. Theta equal to pi plus 2 alpha, theta equal to pi plus 2 alpha. Or in terms of x, it will be sorry sin 2 alpha. In terms of x, it is minus c by 2 sin 2 alpha. This is obviously on the lower surface. Look to then what will be the velocity, I mean the flow pattern. First of all, think that this is what is our flat plate, the flow is coming at an angle alpha, the forward stagnation point is somewhere here on the lower surface, let us say it is somewhere there, it is on the lower surface, it is not at the front point, it will be at the front edge when alpha is 0. For any non-zero alpha, it will be on the lower surface, assuming positive alpha. Then think about say two streamlines adjacent to this. This is of course now becoming this, the body itself, and another streamline which is here. Is following parallel to this body. Another streamline which is ahead of it is going here, then it is turning and again becoming parallel to this. So, these are the streamlines, flow streamlines, or the flow will be like this. The inviscid potential flow about a flat plate airfoil will be like this. This streamline will go here and then will turn back and go round over the upper surface. What is the velocity at the leading edge? Can you find out what will be the velocity at the leading edge? Leading edge corresponds to theta equal to pi. The leading edge of the airfoil corresponds to theta equal to pi, or where x equal to minus c by 2. You can use either. Yes. The complex velocity u minus I v, how much it is at the leading edge? Here also you are getting q infinity cos alpha, is a little bit strange. See, W equal to q infinity sin alpha minus theta by sin theta, and how much is sin theta? Sin pi 0. Then if you take limit, then it is so pressure at the leading edge, how much it should be? Again infinite. Pressure should be 0. Why? That means pressure also you can't define. Velocity is not defined, pressure is also not defined. Meaning that at the leading edge point, an infinite suction peak is created. An infinite suction is created at the leading edge, or the leading edge is basically a singular point in this case. Now, you see that is there any justification it? Of course, this is not correct. If we consider any real flow problem, even flow about a flat plate at the leading edge is not undefined. Usually in a viscous flow, that will be a stagnation point, and or the flow velocities are 0 there also, and pressure will be some finite pressure. The pressure will be some finite pressure, but in this inviscid flow, if you look to this figure, you see at this point, which is the stagnation point, from here then as we move to this side, which is part of upper surface, this part of this, the front part of this flat plate, which is ahead of the stagnation point, this is the stagnation point, and this part on the lower surface, flow velocity is increasing from 0 to something. At here it is becoming something undefined. You are calling it infinite in the sense that okay, this is going on increasing, the flow velocity here is 0 and then gradually increasing, and here it is undefined, it is okay, you are saying very large, because it was very large ahead of it. So, there is a very quick or very high acceleration in the flow velocity over this small distance. This is of course not a very large distance. Over this distance, the flow has accelerated very rapidly to a very high value. Consequently, the pressure here is also, as the velocity increases, pressure decreases. Okay, the flow pressure there decreases. So, if when the flow velocity increases tremendously, we can say the pressure has decreased tremendously or infinitely, minus infinity, okay, and we are calling it suction. So, of course, you can never verify it experimentally, because in experiment you will never get this ideal inviscid rotational flow. You will not be able to create that ideal inviscid rotational flow in an experiment. So, you can never verify this experimentally, but what you can verify that what happens to the pressure or velocity near at the leading edge. If you do that experiment with some airfoils, you will see that at the leading edge the pressure is really very small, really much lower compared to the pressure at any other point, and flow velocity is quite large near the leading edge. And as the thickness of the airfoil decreases, the suction near the leading edge also increases, that is pressure decreases as the thickness goes on decreasing, thickness of the airfoil. So, in the limiting case, when the thickness is really 0, we can accept that okay, the pressure is approaching to a very small value, or the suction there is very large, infinite. But of course, this is not real, but a very large suction near the leading edge is a reality. When we will be doing some experiments and see, we will measure the pressures, you will see that there is a very large suction near the leading edge, and that suction increases as your angle of attack alpha increases, as well as your thickness decreases. For thinner airfoil, the suction is higher. Similarly, at higher angle of attack, the suction is higher. How much is the lift force per unit span? Lift force per unit span we have already derived the general formula for lift force. Or the lift force is rho q infinity circulation. How much is the circulation here? For the flat plate, okay, let us write it at this stage and then first calculate circulation. How much is the circulation? Yes, pi c q infinity sin alpha. Okay. So, the lift force you can straight away write and lift coefficient hmm? 2 pi sin alpha. And see, in practical aerodynamics, the angle of attack is usually quite small. Looking to an aircraft, most of the time the aircraft flies at an angle of attack which is somewhere very close to 1 to 2 degree, okay. Except during landing and takeoff, where the angle of attack is little higher, of the order of some 12 to 15 degree, in that range. Most of the time, or say 95, more than 95% of its total flight time, the angle of attack of an aircraft is usually of the order of 1 to 2 degree, which is quite small. And for such small angle of attack, we can make an approximation which is 2 pi alpha. a very remarkable result. With such a simple theory, the lift coefficient that is given by this 2 pi alpha comes quite close to the lift coefficient of any airfoil. Next, we will consider another case, next case that we will consider. Of course, we can find what we have found here, flow along the length of the plate, flow along the length of the plate. We can find even flow which is normal to the plate. We may try that, how to get it, flow normal to a flat plate. That is, the plate is like this, plate is like this, and flow is coming like this. Okay, for such a situation, this envisaged ideal flow is not a very good approximation, it is very, very poor approximation, but anyway it can be done using this transformation. And you will look how to get this. I will consider, I am not doing it here, you have to look for it how to get it. Okay. The next case that I would like to consider is, again the center of the circle is placed at the origin itself, but the radius of the circle is larger than b, or that parameter b is smaller than the radius of the circle. Let us say this is what is b, b is less than r, this is plus b, this is minus b. That is, the critical points are now inside the circle, there is no critical point on the surface of the circle. So, the transformed geometry will not have any sharp corners, the transformed geometry will not have any sharp corner. At each and every point on the transformed geometry, the angle is same as it is on the circle, that is again pi. What is this body now? Z equal to zeta plus b square by zeta. Zeta is r e to the power I theta on the surface of the circle. What it is? What is this? Oh. Yes. What is this geometry? So, this is an ellipse. With some major axis of r plus b square by r, and the minor axis is half of the minor axis is r minus b square by r. We will not call it major axis and minor axis, rather we will call thickness and chord. So, the thickness or the maximum thickness of the transformed geometry and in analogy with the thickness to chord ratio for an airfoil, here also you can have a thickness to chord ratio, which is also called a fineness ratio. That is, by thickness we of course mean T max. And in case of ellipse, instead of this T max by C, this fineness ratio is a more preferred parameter, which is the inverse of this quantity. So, let us say you are asked to find the solution or the flow solution for an ellipse. Can you say what will be your steps or how you will proceed to it? See, you will be given this either flat plate or ellipse or some other airfoil that you will be getting. Those are the things that will be given to you, not that circle. That is what your job is. Let us say in this case we are saying that okay, we have something which is in elliptical shape and we want to know the forces acting on it and it is also told that the force is only due to pressure. Then what will be your steps? What will you do? Any suggestion from anyone how to proceed? How to proceed? Let us say you are given that we have an elliptical strut, or let us say an elliptical column, and a wind is coming to it at facing such an angle at such an speed. Find the load that is acting on this column due to this pressure. So that ultimately you are going to construct that column. How you are going to use this knowledge that we know the solution of the flow solution for ellipse provide from the known solution on circular cylinder. How you are going to use it? Because that is what is your problem. No one is going to ask you, okay, we have a circle and in that center we have a doublet of this strength, of circulation of this strength, and find this pressure on this circle. No. The problem is this. Let us say think in terms of aircrafts only. Someone says that the landing gear of an aircraft are elliptical in cross section, and then the aircraft is running on the ground, so that at such a speed the flow is coming to this landing gear at such an angle of attack. To find the pressure acting on this landing gear, so that you will be able to find how much it should be, or what type of material you should use, what would be the strength of that material. So, how you are going to proceed? You know all these, okay, how much is the flow velocity, you know all these formulae, everything. You will convert R and V. Where are you getting R and V? See, as far as the flow over a column, let us say this column itself in front of you, of course, it is not elliptical, it is rectangular, is concerned. Where is its R or where is B?
We are converting R and B into in terms of C and D.
Okay. So, knowing T by C or the fineness ratio of the ellipse, since that ellipse is known to you, you see that is the reason, see in our transformation, if you look to the other, we are showing it this way, that transform from Z to zeta, not zeta to Z. See here also. So, okay, if you know about the ellipse, let us assume that you know the fineness ratio of the ellipse, that will give your B by R first of all. Okay. If you know now the R, you know what is the doublet strength for the flow about circle, okay. And applying that Kutta condition, you can also find what would be the circulation. Then you can write what is W zeta, and once you can write the W zeta, next of course everything comes straight away. So, the velocity and any other of course you can find here. Once again in this case, since there is no critical point on the circle, you cannot satisfy Kutta condition and you cannot say what is circulation. So, this flow will either be treated as non-lifting, there is no circulation, or there will be some other condition given from which you can find what is circulation. Just as it is, we cannot apply Kutta condition because there is no sharp corner on the ellipse. On the ellipse there is no sharp corner, and hence we cannot find what would be the rear stagnation point on the cylinder or the circle for a given case. That is essential to have a corner where we can satisfy the Kutta condition, trailing edge at the corner. For an ellipse there is no trailing edge corner, so we cannot satisfy Kutta condition, we cannot say what is circulation or how much is it. So, it will remain unknown as in case of original cylinder. However, it will be usually treated that it is non-lifting, like circle is usually, cylinder is usually non-lifting, elliptical cylinder will also be treated as usually non-lifting, there is no circulation, or something else must be given, which will fix the value of circulation. Unless those are given, you cannot fix the value of circulation in this case. Okay, we will consider few other specific cases before we moved on to something.